All right, let's dive into something pretty wild today. We're talking about a full-on scientific rebellion, a story that takes a shot at a 2,000-year-old truth and could end up rewriting the rules of science itself. And it all starts with the tiniest thing you can possibly imagine, a single point.
I want you to think way back to your old geometry class. Remember being told that a point has a size of 0? That it's got no length, no width, no depth, nothing? But what if that idea, that core assumption that's been the bedrock of physics for literally centuries, was just wrong?
You know, for over 2,000 years, everyone just went with Euclid's definition. A point is something that has no part. It's simple, it's elegant, it feels right. But here's the thing. In modern physics, that beautiful idea turned into an absolute curse. As soon as scientists started treating things like electrons as zero-sized points, their equations just exploded. They'd spit out the number infinity, creating this massive roadblock right at the heart of our understanding of the universe.
So that brings us to the first part of our story, the disaster of zero. We're going to look at how this one tiny, simple idea of a zero-sized point created this domino effect of problems for science. It was this massive error hiding in plain sight for thousands of years.
So what kind of disaster are we actually talking about here? Well, for starters, if an electron has zero size, the math says its own energy should be infinite, which, is impossible. In quantum physics, the equations that were supposed to describe reality just flat out broke. They'd lead to total nonsense. And then there's the big one, black holes. At the center of every single one, this idea created the singularity, a point so infinitely dense that our laws of physics literally just give up.
So faced with all these impossible infinities, what could the scientific community do? They couldn't just throw up their hands and go home. Instead, they got creative. They came up with a very clever, maybe not entirely honest workaround to just keep things moving.
And that workaround has a name. It's called renormalization. And what it is really is a kind of mathematical trick. See, when the equations would spit out these ridiculous infinite numbers, scientists figured out a way to basically just chop off the infinity part. They'd subtract it from the equation to force the math to line up with what they were actually seeing in the real world.
Okay, here's a good way to think about it. Imagine you're making ramen, and you accidentally dump in way too much salt. Instead of starting over, you just pour out half the super salty broth and add fresh water until it tastes right. Or, it's like a soda that's way too sweet, so you just add a bunch of ice to water it down. It works, sure, you get a result you can actually use, but you never actually solved the original problem of why there was too much salt or too much infinity in the first place.
And for decades, this was just how things were done. Renormalization was this brilliant patch that just covered up a massive fundamental flaw. But then, a direct challenge to that 2,000-year-old idea finally arrived, and it came from South Korea.
Now, this wasn't some lucky overnight breakthrough. No, this was the result of a 35-year mission by director 양동봉. To even attempt this, he had to invent entirely new tools from scratch, a whole new mathematical system called OPS, and this incredibly powerful analysis tool called the AI Buckingham machine. With these in hand, he set out to calculate something everyone else thought was impossible to calculate, the actual, real, finite size of a point.
So, after all that work, what did he find? First up, mass. The calculation shows that a fundamental point isn't massless at all. It actually has a mass of 10 to the power of negative 134 kilograms. I mean, just try to wrap your head around that number. It's so small, it's basically unimaginable. But here's the absolute crucial part. It's not zero. It's a real thing.
Okay, next up, its actual size. The answer? 10 to the power of negative 95 meters. Now, to put that in perspective, for decades, physicists thought the absolute smallest possible unit of length was something called the Planck length. This calculation points to something that is trillions and trillions of times smaller than that. It's like discovering a whole new universe hidden inside of what we thought was the smallest possible speck of reality.
And finally, time. It turns out a point exists for an incredibly brief moment, 10 to the power of negative 104 seconds. So, once you have these three finite, real numbers, a specific mass, a specific length, and a specific time, the whole concept of a zero-sized point and all the crazy infinities it created is claimed to be completely solved.
Think about it. If a point has a real, finite size, then all those infinities that have been plaguing physics for a century, they just vanish. This isn't just a small correction.
This could be the start of a whole new era in science. What the source material we're looking at is calling the K-science revolution.
And there's a history to this kind of thing. Back in the day, Newton's laws made the UK the undeniable center of the scientific world. Then, Einstein and relativity came along, and that center of gravity shifted over to the US and German-speaking countries. So the question this discovery raises is, who's next? Because the nation that sets the fundamental rules of science has always been the one to lead the world.
So let's just break down what a huge shift this is. The old way of thinking started with a point particle, which led to the infinity problem, which forced scientists to use the trick of renormalization. The new paradigm starts with a particle that has a finite size, which provides a fundamental solution to the infinity problem. No more tricks needed. It's a clean fix.
Okay, so this is all really cool, mind-bending stuff for physicists. I get it. But you might be sitting there wondering, why should I care? Why does the size of some impossibly small point actually matter in the real world? And that's a totally fair question.
Well, let's look at it. For scientists, solving a problem this fundamental is the kind of thing that Nobel Prizes are made for. For the nation, this is about building the K-science brand, a new source of global prestige. For education, it could mean future textbooks around the world will literally say the size of the point was first calculated in South Korea. And for investors, listen up, because this isn't just theory. The AI and the mathematical models built for this research have direct applications for designing next-generation semiconductors and artificial intelligence.
Now, the source material also links this achievement to a bigger national vision. It lines up with the Stronger Korea agenda, which has been emphasized by political figures like Lee Jae-myung. The idea here is to establish what they call scientific sovereignty. That means having the power to actually define the rules of science for the world, not just play by someone else's.
At the end of the day, this whole thing is just a powerful reminder of how science is really supposed to work, right? It's not about memorizing a bunch of facts in a book. It's about having the courage to question them. I mean, every great leap forward we've ever made, from realizing the Earth goes around the sun to Einstein's relativity, it all started because somebody dared to say, hey, what if this established idea is wrong?
And so, that's the big question we're left with. We've seen the torch of scientific leadership get passed from one nation to another throughout history. With a challenge this fundamental, aimed at the very language of science itself, are we watching the beginning of the next great shift? What do you think?